Yeah. Yes, sir.
Good afternoon. My name is Rashad Saxena. I'm a third year BSc student, a BSc blended student at the Interdisciplinary School of Science, Savitribai Phule, Pune University. And I will be talking about a Python pipeline to analyze 21 centimeter H alpha spectral line data from a horn antenna. So this will be on the data that we have captured from a horn antenna at the Ayuka campus. Oh, okay. Great. So so my mentor for this project was Ashish Mahaske from Ayuka. So before we discuss the pipeline, why didn't the screen? Okay. Why isn't this? One second, I'll just unshare and share again. It happened, right? Okay, maybe it's lagging.
Yeah, there's a line. There's a line.
Okay. One second, I'll share again. Yeah, okay. Yes, so we'll just discuss briefly what is the 21 centimeter neutral hydrogen spectral line. So basically in the interstellar medium where the temperatures are very low, a nascent oxygen or the single hydrogen atom goes through a energy phase transition, which happens when both spins are parallel, and what happens is one of them becomes anti-parallel. And and when this happens due to the energy transition, we have the release of a radio wave, and the frequency of that radio wave is 1420 megahertz, which is roughly 21 centimeters. So, and this is used by astronomers for finding the rotation curve, velocities, etc. So, where is this neutral hydrogen present? The answer is all around our Milky Way. So, if I don't think it's very clearly visible in this, but if you can see, there are certain lines and there are certain angles marked. So just note those angles. So like here you can see it's 120 degrees. So all of these are called as galactic longitudes. So just remember them so that when we discuss the data set, it becomes clear what am I talking about. So yeah, we'll move on to the next slide. So yes, so just a fun fact. So this transition that I was talking about happens once in 11 million years of a hydrogen atom's life. So, and the interesting part is we continuously get this 21 centimeter radio waves at us. So this just shows how abundant hydrogen is in our universe, that we are getting continuous so-called supply of the 21 centimeter radio waves. So how did we capture these radio waves? So we using the horn antenna that we have at the teaching learning center of Ayuka. So this is a horn antenna, and we captured the readings for different galactic longitudes over the summer. So sadly this time in Pune, the summer had clouds. So, but luckily the radio waves just could penetrate through the sky, and we could the clouds, and we could still take observations. So even though our optical things were completely off, but still our horn antenna was going good. So this is me with the horn antenna at the Ayuka, at TLC at Ayuka. So I'll just briefly describe what we do. So basically, we have to take a few calibration readings. First of which is taken from the sky. So we point the telescope anywhere randomly at the sky. The second reading is we point the telescope at the ground. And the third reading is not a calibration reading. It's actually a reading of the source. So we choose either of the galactic longitudes that are shown in the earlier slides, and we observe it. So, and how do we observe it? So we have an entire backend electronics that helps us. So this is the basic circuit diagram. So basically the horn that you see in the image, that is the horn. Then it is connected to a low noise amplifier, which is then connected to a bandpass filter, And for a coaxial cable, it goes to a SDR, which is a software defined radio, and then to a computer. So one second. So all the LNA and BPF that you see in this image is actually this electronics, and the cable that you see is the coaxial cable. So we'll just so before we actually look at the actual Python pipeline, what it does and what we are actually doing, we'll just quickly discuss this relation. So P equals to KBT, where KB is the Boltzmann constant and P is the spectral power. So using this, one can write relations like this. So as I said, we take readings from the ground, the sky, and the source. So the P ground is corresponding to the power through the ground. P sky is of the sky, and T source is of the source. Then one thing that we didn't take into account is because even though when we say there is no sun, there is ambient heat. And due to this, our receiver or overall the antenna has a certain temperature, and this is accounted as TR. So whenever we measure something in, so we are not purely measuring the source, we are also detecting some of the receiver's heat, which is TR. Okay. So using that, we can write the equations that you see on the top, the two, and then using them, we can, so basically we have two equations and we have two unknowns that are TR and T source, and just we can make them the subjects and reduce the value of TR and T source, and using which at the end what we want is the T source. So generally the pipeline that we have written, normally to analyze the data, it takes almost a day or two to analyze the entire thing, but with this pipeline, you can do it within 15 minutes. And I say it's a pipeline, and you might think it's something very, very, very cool or something that is something completely new, but it is just simple Python and analysis and multiplication of NumPy arrays. So before we actually, we'll have one more relation, that is this is actually so basically what we observe is the bands of the Milky Way, and we know the bands of the Milky Way are actually moving. So instead of just velocity, we actually measure the Doppler shifted velocity. So this is just the equation for the Doppler formula, and this weak core. So basically we have to add for the correction due to the movement of the Earth on its own axis and around the sun. So while we are on the axis, we have to consider the latitude and the longitude of the observatory, and also the altitude. And so basically we have a Python code which will give us the V core, and using that we can actually calculate it. So I'll now show you the pipeline. Yeah. Yeah. Okay, I can actually show you the data also. So this is one of the data that we have. So this is the data corresponding to, one second. Yes, okay, good. Yeah, so this is one of the data that we have corresponding to the 70th longitude. So basically it has the date, it has the time. Okay, okay, I've actually opened up an older data, but it's okay. So it has the date, the time, the starting frequency, the ending frequency, and the step size. And after that, it has the power, which okay, that's not cool. No mind. It has power in dBm. So when we start, so basically we start with converting this power into watt. So this is all the packages that I have used. We declare a few constants that we have used during the entire thing. And so, yeah, so this here actually, so we just, when we get the data, there is no frequency as such that is defined. So we have to generate an array that has all the frequencies. So this part of the code is doing that. Then using these frequencies, we generate the velocity, which is then corrected here. Then here we are importing the ground data. And yeah, so here you see this line because I had to ignore the first 6 elements, which were basically which carried the information of the data, which we didn't need. We just needed the power. So that's what that's why we ignore the first 6 things. Then we convert the power that is in dBm into watts, and that is being done here. And then the formula that I showed in the PPT, using that we calculate the value of TR. And then the value of TS, and we get this graph, which basically shows the increase in temperature. And but there is one slight problem in the entire thing, because this neutral hydrogen is so abundant in the entire galaxy, and we're basically surrounded by it. So when we take a random sky calibration reading, what actually happens is we get a peak due to the ambient hydrogen present, and due to this peak we get a sudden dip here, which we don't want. So what we do is we take a few, okay, yeah, the curve is visible. So we can take a few values from here, take a few values from here, take their average, and actually draw a straight line and cut off the curve. So that's what is being done here. So this peak that you see is being cut off, and then we recalculate the value of T source, and that is called as T corrected. And you can see that the T it's all smooth now. And yeah, so and here what we can see is it's at base 10. So to bring down the entire curve, we'll just divide the entire thing. Subtract the entire thing from the average, and then the entire thing just comes down. And to actually get to fit the curve, we simply do a Gaussian fitting, and after that we get the fitted curve. And to actually see which the actual Gaussians that are fitting the curve, we have actually printed the Gaussian, so that we can have an clear idea that what Gaussian is doing what. And then after that we calculate the residuals, and this is important because the better this thing should look like a noise. So till the time it does not look like noise, it shows that your curve is not, your fit is not perfect, and that is what is being shown here. So because it looks random and noise-like, one can say the fit was good. And yeah, so all of this next steps are done to actually find the rotation curve of the Milky Way, the bands of the Milky Way. So so here basically we find the most redshifted point to later find the rotation curve of the Milky Way. And that is the entire pipeline, that the so-called pipeline. And yeah, so thank you.
Questions?
Oh, okay.
Questions?
Okay.
Questions? Hi.
Hello everyone, this is Priya and we saw some really exciting presentations today and throughout the workshop. And since the whole workshop is based on astronomical data analysis with Python, and actually, truly speaking, I am not a physics guy. I am a computer science guy who has dived into, who is trying to dive into astronomy. So what I found is that during data analysis, many astronomers need to do coding with Python. And I believe it is not necessary for them to know everything about coding, because they have to dive into this programming language, they have to know everything, and then they have to do physical interpretation for that. So I think that that is a bit problematic for them. So if there is something that we computer science guys can do for you people, for this community, so I think that can be helpful. So here is something called EDA tool for astronomy. Actually, this is not a presentation, to be very specific. This is a proposal that I am giving for collaboration actually. So just a few days ago, this I felt that it can be useful, and if you people can help and collaborate, we can make something to contribute to this community. So the thing is that in our there is some machine learning life cycle in if we talk about machine learning in particular, because we generally use machine learning for data analysis. So first what we do, we just take the data, gather the data, then we go for data cleansing, because the data that we are receiving, it can have some outliers, it can have some null values, so we have to somehow deal with that. So that is a different thing how we are dealing with that. But and then there comes something like data formatting. We may have to convert some columns. We need to merge some columns and make some new columns. That those things we need to do. And there are other things which we call that exploratory data analysis. The term exploratory data analysis is not exactly what we do to fit a model. Actually, it is a thing that we do before fitting a model. It just gives an insight of the data that you are using. For example, if there is some data on anything, it can be, for example, it is on the radiation or on the luminosity, or it is on the dispersion measure, anything. So first what we do, we just take an insight of that, what is in that data, how we can work with that data. So what we normally do, we make a histogram, we see whether there is any correlation with some other variables or not. So all these things, as you know, it comes under exploratory data analysis. So here is a proposal that if we make a tool that will just do exploratory data analysis for you, and then definitely you have to do some other things according to the need, but it will do the exploratory data analysis for you. And suppose as I told, there is some data for dispersion measure. So it will just look into that data. There you have a CSV file or FITS file or anything. It will just dive into it. It will just automatically give you the exploratory data analysis. When I tell the term automatically, I mean it will generate automatically. That is, nowadays we are all familiar with generative AI. I think most of the people will be familiar with ChatGPT or those kind of generative AIs. So this thing is going to be a generative AI web-based tool. So you do not need to mention whether you need a histogram, whether you need an ANOVA test, whether you need some correlation test or a Gaussian. You do not need to mention that. It will have some basic kind of intelligence. It will look into that, and then it will suggest that these are the things that it felt important, and it will give you the thing. Definitely, it will not be 100% correct, but it can help you up to some extent. There can be some times that we might ignore that these things were there. Suppose there is a histogram, and we might, while fitting the Gaussian, we might just ignore some values at the extreme ends. So it can also just zoom into it, make a Gaussian fit there, and what you can do for that particular small Gaussian fit there, you can try to give a physical significance for that. So in that way, it can be helpful. So here are the few. Sorry, it is not responding. Yeah. So there are the 10 proposed things that this application can help you with. It can help you with data cleansing, data formatting, then univariate non-graphical analysis, univariate graphical analysis, multivariate non-graphical analysis, multivariate graphical analysis. All these things Then there comes classification, clustering problems. It can be a time series analysis thing. It can help you with that. And if possible, we can also try to make some, this particular software can help you with simulations. Actually, we have to dive deep to make these simulations generative. So the thing is that how can we make this thing a generative? So this is a preliminary requirement analysis that I have done. So first of all, we need to do feasibility analysis, how much feasible this thing is. So then we need to gather the information from astronomers who are really going to the users of this particular application. We have to gather the information what they exactly need when they do data analysis, when they do this particular job. Then we will need an excellent team for carrying out this job. It will be comprising of astronomers, definitely, statisticians, mathematicians, then some people who have really good expertise in generative AI. Definitely, since we are going to deploy it in some server and it will be an web-based application, so we will be needing some front-end developers, then some DevOps engineer. When I call the term DevOps engineer, why do we need that? Because since we will be delivering this thing in an incremental way, we are not going to create the whole software in one night and then deploy it to the server. We will be, for example, first we are going for histogram, then some other team, there can be many teams, so some other team is working on some parametric or non-parametric test. So we can just keep on incrementing the thing, and in that way we can finish the work. And there are some software tools that we might need to create this. And one thing that I forgot, that regarding that, suppose it is creating a histogram, but to some extent you are feeling that the bin size is not according to what you wish. So what it will do, it will also give you a window where it will just generate the Python code for that. It will be interactive as well, because if you go there and do required edits, so you can also change the things that you need to do. If you need to change the theme, you can change that. If you want to add the grids, you can do that as well. So in that way, you do not need to write the code from scratch. You can just, it will just give you a code. You can, if you need anything, you can just add your code over there. And then I think in that way, it can help you, it can save the time. And definitely we will be doing this whole thing in Git, and we will be using CI/CD, that is continuous integration and continuous deployment. So in that way, we will be moving towards agile DevSecOps methodology. And the time that it can take, I don't know how much time it depends upon the team, how many team members we will be getting, and how much effort that we can put together to make this a reality. So what I believe is that if we get a really big team, we can finish the work in 24 sprints. That 24 sprints means we call sprints, that is we take 10 to 14 days, that is 2 weeks. We call it a sprint. So within 24 sprints, I guess it is coming to be nearly 1 year. We can finish this work. At least we can start from a very simple problem, and I guess in some way it can help you with that. So that was all that I was willing to say. This is just a proposal for the collaboration. If anybody wants to collaborate and work on this particular thing, so please let me know. We will form a team and we can just contribute to that. So that's all. Thank you. If anybody has any questions.
On the whole, I agree, your steps are very good. It's all very nice and all good. But the problem is that this is broadly the steps which we do. But the thing is that depending on which wavelength, what is your purpose, what are you doing, the whole thing changes, right? So it's really difficult. So one is you do pandas profiling, regular data exploration, that is fine. But otherwise, all these steps will vary a lot depending on the distance. For example, you are doing the project with Kushan Map, right? So for your data, there'll be a certain way you run the steps. But for example, one was doing exoplanets, then your steps will all change, right? So I don't know. You want it to be in a general form or you want it to be in a specific form?
Actually, this since it will be a generative AI, so if you we can also keep a text box for that. Suppose you want some box plot or some bubble plot. So you can just suggest the model that whatever you are doing, just include these two as well. So it will also give you that one also. So since it's a generative AI, it will have the intelligence. It can take the inputs what you suggest. So it can help you with that. And after generating the plots, if you feel that at some point it is just excluding some points, or it is doing some mistake there, or the color code is not good, you can make the required editings there. So that is the thing. Yes, sir.
See, the idea is very good, but there are already certain tools which have been created, which have been used for astronomy. Like Topcat is there, then virtual VO plot, VO tables, there's many, gamut of things which have been already developed. Right? But this is a good exercise. You can maybe take up a specific problem and build one on that first one. And then you can also do this.
That can be a prototype.
Yeah. And then specifically for each research group in PRL or in University of Hyderabad, or you are doing something specific, then you can keep modifying it and giving it. And it will be very useful for that set of people in that set of people.
Definitely.
So specifically models you can make, one for say cosmologists and some for star people. But you can start off with one specific problem which you know. Say the one which you are using working with Shushan. On that you build it up. See the issues, difficulties which come up. And how to fine tune, and then that can be very helpful for the whole set of people to do that kind of stuff.
Definitely, sir. We will do that.
But it would be good idea. I would just add what Matt said, that suppose I'm working in radio data, it would be a bit different. It comes in Fourier space. So before even coming to data analysis part, I have to first reduce it to normal space and then come to.
Yeah, actually, I have not mentioned properly there. When I call it data formatting, I should have mentioned that if there is some sort of space, you can convert it to some other space. That is, if you want to draw it to kernel space or anything, if you want to do, if you need to reduce the data to some other form, so you can also do that. So we will be giving, actually it is aimed at that point only. So we will be helping you with that. And regarding after this process, you can just go for data fitting. That is after that, all sort of these things, what we do is that we go for fitting a model. That what model can define our this particular data or our problem statement, what can be the equation for that. That is a different part of thing. And so after running this part, we can move over there. Actually, since if we keep a input box there where you can suggest that do this plot for me, it can give you that plot. So you can give a series of those plots. So in that way, you can it can also help you with model fitting as well, I believe, if we can do it perfectly.
It's not only about model fitting, but before even we start with analysis, there will be many steps. We're working processing, in cleaning, in CASA, we need at least 5-6 times of cleaning before we could just. And then for every specific group, yeah, you can get money. Yes. So last
5 steps probably can be a separate packet.
Yeah, that will
Probably
be
post data processing unit for analyzing that.
definitely, that will be
That
after
can be a
that,
different packet.
definitely, it will be like that
That would be,
only.
I think, my suggestion.
Yes, actually, it should be like that only. I should have made point A, then point B, and all those data analysis should have gone to point B. So actually, I have made it in a hurry. That's why it's not in that perfect format.
That's a good idea.
Yes, sir.
That's okay. So the same says having it as a global package is not going to work. Individually, if you make for the particular dedicated group, that's the going to be the way out. Because even in the same field, persons are working, different groups do implement their operation in a completely different manner. So it would be helpful, but like the way we were talking about parametric, non-parametric methods. Over there, the moment you will come up with a new data, the whole structure, the way you will develop the program, that will also change. So there can be a tool which you can use for doing any analysis, but there is going to be a whole complete channel that will depend on problem to problem.
Definitely, sir. We
that
have to
way
be,
you can use small groups, use one problems and focus on that. Make the whole package for them.
we have to be case specific every time. Okay, sir. So that's all. Thank you, everyone.
And it can have a lot of commercial interest also, that it can be done for schools and if people do, they create a whole logistics. Everything which is attendance and salary and this. So once you know how to handle data and how you can go about it, you can become a, people learn how to do it, especially. It can be used for a variety of different.
Yes, sir.
Any more suggestions, please?
Yeah, please.
Yeah,
Like when we have a large data sample, like for individual sample, we can choose whatever we want to do, right? Or when we are talking about a large data sample. So it will be very important for each data will be behaving, each set of data will be behaving in a
Differently.
way. So it is important for us to choose which data should be undergoing this process and which data should be undergoing this not, this process should not be undergoing this.
Actually, yeah, it should be case specific. It should behave according to your problem statement. What is your data? Depending upon that. That's why we are using generative AI for that. It will analyze and then it will suggest. And if you have specifically some suggestions that it should work on this particular things, so it will also do that. So that is the basic idea. So if anybody is interested on this, so we can collaborate and work, because what I feel is that this is a big job and a small team cannot work on this. Otherwise, it will take a huge time. That's the thing. So, okay, that's all. Thank you.
yeah, actually what